So this is the example of the seasonalize the data from 2016 to 2017 by the table number 1 given. So what I've done here, I just cut the table, and instead of, as you guys can see here in this section, what I've done is, instead of just giving the letters, what I've done is just change it in for numbers. So this will be January, February, and so on. Then what I've done is just copy and paste the data. So when we talk about the seasonalize, what we're trying to do is to smooth out the data frame so it takes away some of the seasonal fluctuations of original data. So to do this, we need to start doing the seasonal indices. And firstly, what we do is we do the average of one of every year. We know that we're talking about the monthly unemployment rate, so we take the average every month per year. So what I'm trying to say is we take the data of this, all these months, we add them together and we get the average. So we know that the average is the addition of all the individuals sets of data. So for the first month we got 6.5 plus 6.2 plus 6 plus 5.7 plus 5.6 plus 5.5 plus, and so on onto our last data, which is 5.6, all that divided by 12, and that will give me the average, or we call it as well, which is the mean, but we call it average. So that is our average of the first year, which will give us a number of 5.08, and for the year 2, which is 2017, is 5.583. So now once we find the average, what we do is find the indices of every year. So if we want to find the index for the first month of 2016, so we do 6.5 divided our average, which is 5.708, and that will give us a result of 1.138. This is what we call the seasonal index, which is the actual value over the average. So once we go through the whole table and we find the seasonal index for every month, that's what we get. So as we said, we take the actual value for every month of a year and we divide it by the average of the year. So you get 2016 seasonal index and then 2017 seasonal index. Now what we need to calculate is an overall seasonal index for both years. So we know that we have 2016 and 2017. So we need to have now an average seasonal index, if you want to call it like that. So the seasonal index for 2016 and 2017 for the first month will be 1.13 plus 1.9 divided by 2, which gives me an answer of 1.115. Sorry. So then you do the same values for every month. Yeah. And this is what you get. And this is what it looks like at the end, the seasonal index overall of 2016 and 17. A handy rule to know is that the seasonal index numbers will always add up to the total of periods you have. In this case, this is a seasonal index, and if we add all these values of this column, we will have a total of 12. Once we worked it out, the seasonal index of the 2 years, now we're ready to deseasonalize this data. And the way that we deseasonalize this data is just following a simple formula, which you find it in your textbook, which is to deseasonalize figure equals to the actual value of your data over the seasonal index. So for our first value, so for month number 1, deseasonalize, of course, the actual value for 2016 is 6.5. I'm looking at this one over the index season of that month, which is this one here, 1.115, which gives me an answer of 5.826. So once you do that for every month of the year, you get this set of data. So I just put D as deseasonalized for 2016 and D, this is a D guys, for 2017. So when you plot the original values of months and 2016 and 17, this is the graph that you will have. You notice that there's some fluctuations in the graph, which it could makes it a little bit harder just to read and to predict and do some predictions with it. So that's the reason why we deseasonalize as well this data, so we can just see the trend of this graph. And once you also plot the deseasonalized set of data, which is this one here, the 2016 and 17, you will get this orange graph here. And this graph, the yellow one that I just underlined, help us to do some predictions of the data with the deseasonalized plot. And once we put our data into a graph, we can analyze as well the data. And if you see in the last picture that I just pasted, we have an equation of that data, of that set of data, which is y equals 5.75 minus 0.008 x, and that represents our y-axis. It's our deseasonalized equals 5.75 minus 0.008, our period. And there you go. You get the equation of that last deseasonalized graph. Then with our last equation, we can answer the next point of question 4, which asks us to find the least squared regression line the equation that can be used to forecast the future unemployment figures. And this is the equation that we can use to forecast that future unemployment figure. In the next point, they're asking us to do the forecasting for January and February for the following year. So if we said originally that 12, it was our first year, 24th will be our second year. On the month number 25th will be January of the third year, and so on. For 26 will be Feb of the same third year. So what you do now, you just replace in the equation 5.75 minus 0.008 for a value of, in this case, for equation is 25, because the data here will be 25th, and also for the value predicted for February. Which you will get for the first one an answer of 5. Let me just do it with another color. 5.54, and for this one 5.54. So now that we found these two values, those values represent the deseasonalized value of this set of data, which means that this is not the original value that we're looking for. So to do that, remember the equation, which is deseasonalized equals to the actual value over the seasonal index. So in this case, we know the seasonal value, which is 5.54, because it's the one that we just found. What we're trying to find is the actual value, and this value of the index, we have to go back to our table, and if we go look here, remember we said this is January, and this is February. So we have an average of seasonal index for these 2 months, which basically represents these two. So if we use those seasonal indexes to predict our actual figure, so for January will be 1.115. We go back to, so we rewrite this again, 5.54, 1.115, the actual value. And then if we use that, we put that in our calculators, 5.54 times 1.115, it gives us an actual value of 6.177. That will be our value for January on the third year, which is 6.177, which is the unemployment rate for that particular month on the third year. And if we do the same for February, we just need to replace the value. So we just do 554 equals the actual over the seasonal index, and we just said that we're gonna use the one that we found for February, which is 1.107. Sorry. So that will give us 5.54 times 1. Sorry, I forgot. 107, and it gives us the actual value, and the answer is 5.92. So for the third year on February, we have a unemployment rate of 5.92. So now what we can see is that if we look at these values, these two, and we look at our table, so by 2018 in February and in January, so we got from the start in 2016, we got 6.5, that's 6.1, then we're gonna have 6.177. So it kind of like remains the same. Well, not remains the same, it actually has decreased. Sorry. And if we look at February 2016, 2017, and then 2018, so we got 6.2, 6.3, and then we got 5.92. So it seems that with the years, the unemployment rate starts to decrease. Okay, guys, so I hope that this has helped understanding this question. And well, we'll see if you guys have any questions, just let me know. Thank you.